Alright guys, welcome back. This is Professor Hank, and in this video I'm going to walk you through the remainder of Chapter 5. Right? Hopefully we'll be able to get through this in a reasonable amount of time. I'm going to try to keep the video limited to no more than an hour and 15 minutes, which would have been the equivalent of a normal meeting for us. And that way we'll be prepared and ready to go for a discussion on our next meeting. We can start off with Chapter 6. Okay, so if I remember correctly from last week, we had just completed 5.4, determining, the AI, or how the AI is going to work using the Minimax algorithm for deterministic games. And so now the text takes us into a discussion, picks up with a discussion with stochastic games. Okay, so let's just dig right in and get through, get this thing finished off. So, if you consider a game like chess or checkers or reversey, those types of games, I guess Go too, right? Go, there's no random chance in Go, if I remember how Go's played. But anyway, certainly for checkers and chess and Othello, right? These are games that are purely deterministic. So what does it mean to be a deterministic game? It means there's no chance involved, right? I take my move, you take your move, I take my move, you take your move. And there's no randomness in it. There's no random chance to it. There's no die rolls. There's no spinning a spinner. There's no drawing a card from a deck. I mean, it's just, the rules are known. It's fully observable. And I just choose where I'm going to move my pieces around. Okay, now, that's opposite of what a stochastic game is, right? So what's a stochastic game? Well, a stochastic game is opposite of that. There's random chance built into it. So you could have some die rolls. You could have, drawing cards from a deck or two or three or four. Maybe a spinner to determine how far you're going to move, etc. Right? So games that have random chance built into them are referred to as stochastic games. So, example, in this section, textbook bases its example of stochastic games and AI for it using backgammon. Okay, fine, right? Because you have to roll 2 dice to determine how you're going to move your pieces around the board. But of course, there's other examples, Monopoly, where you're rolling dice to see how many spaces you move. Yahtzee, you're rolling those 5 dice. The game of Sorry, if you've ever played that, it doesn't use dice, but there's a deck that you draw from. Poker, anything where there's some random chance built into it is a stochastic game. So in the case of backgammon, you've got 2 players, one's black, one's white, and the black player can know where all the pieces are on the game board, right? So all the chips for the black player, all the chips for the white player, they're on the board, they're in their respective positions. But as soon as it's white's turn to move, where they're going to move is going to be random, right? To a certain degree, because there's going to be a random dice roll. There's going to be 2 dice that are rolled, and each one of those dice combined provides a combination that allows for certain legal moves that the white player can make. And so black player is not going to know or can't predict ahead of time exactly where the player could move or where they will move. So because of this, we can't have the same standard kind of game tree that we had with deterministic games, right? I mean, you can just kind of brute force deterministic games and play out the entire game move for move until the very end. You can't do that in the same way with a stochastic game because there's chance involved, right? I mean, you can't know ahead of time exactly how it's going to play out with games where you have die rolls or other random mechanisms for determining what's going to happen. So we're going to need to modify our algorithm a little bit to take that into consideration. So anyway, the backgammon example, figure 5.10, is from the text is laying out a typical backgammon position, right? So you want to move all of your pieces off the board. That's the goal. So white is moving clockwise towards the position indicated on 25. I mean, you would move clockwise going from 7 to 12 to 16 to 21 and then finally off board on 25, just in that direction. And then black does the opposite, going from the direction of 24 to 18 to 8 to 1 to 0, right? So there you go. And a piece can move to any position unless a position has multiple opponent pieces there, right? So if I'm moving clockwise and I'm white and I have these 3 pieces on the number 3 position, right, and I roll a 1 on one of my 2 dice, well, I can't move any of those 3 pieces into position 4, right? That'd be an illegal move because I'm blocked, because there's multiple black pieces there, multiple black pieces there, right? My opponent has multiple pieces on a position already. So let us say, and also if there's just one opponent there, I should mention too, like I could move from 3 to 10, and if I move from 3 to 10, then what basically happens is that my white piece replaces black's piece on 10, and then 10 has to, that black position, or that black piece on position 10 has to move back to its starting position, right? But anyway, so if white rolls 6 and 5, here are the legal moves that they could make, right? I could move a chip from position 5 to position 10, fine. I could move a chip from position 5 to position 11, fine. I could move a chip from 19 down along the bottom to 24, fine. I could move one from 5 to 10, fine. I could move one from 10 to 16, fine. Let's see here, what else could I do? And I could move from 5 to 11. I could move from, then I could move that piece from 11 to 16. So in those cases, in those last 2 cases, what I'm doing is I'm moving the same chip twice, right? So 4 options. The black player would not be able to know with certainty ahead of time which one of those moves I, as the white player, is going to make, right? That's the problem. And so we have to take that into consideration. So in order to do that, our tree is going to have to be modified. We're going to have a tree that's going to contain what are called chance nodes, and these are going to be in addition to the usual min-max nodes that we had from the previous min-max algorithm that we studied. So what are they for? They're inserted into the tree so that way we can consider what all of the possible dice rolls could be, right? So if you take a look at figure 5.11 here, we've got a schematic for a game tree for that backgammon position we just took a look at. So you can see that you've got the different levels, the different plies playing out, but inserted, interspersed throughout the tree, there are some new levels. Then there's levels representing these chance nodes, right? And so if you take a look at the one for min, right, the 3rd row, you see one of these chance nodes has been expanded into possible positions for min, right? So if you look at along the top of the min nodes, you'll see some numbers there. You'll see one, ratio 1/36, 118, 136. Underneath that, you'll see some numbers separated by commas, 1,1, 1,2, 6,5, 6,6, right? So what does this mean, right? Well, what it means is that we have a 1 in 36 chance of us rolling a 1 in 1, rolling snake eyes, right? And so that could lead us to a particular state that min would have to choose, right? Now, the next node over, 1/18, 1,2, what does that mean? Well, there's a 1 in 18 chance that the die rolls came up a 1 and a 2, right? And so the ellipsis there is indicating, well, yeah, I mean, if this is going to be a series of nodes, I mean, we can't account for all the nodes that can be generated in the figure. It's just not enough room, right? But anyway, so this is trying to account for if you roll 1 snake eyes, if you roll a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, a 2 and a 1, a 2 and a, right? So I mean, there's a lot of options there. So you have a 1 in 36 chance of rolling double 1s, and you have a 1 in 36 chance of rolling double 6s, and everything else is a 1 in 18 chance, right? So in figure 510, this shows a position that has a 6 and a 5 that was rolled. So that's going to correspond to a chance node that spawned, min's possibilities, right? And so it just came up 6-5, right? So since it came up 6-5, then that means that we're going to have some additional chance nodes that are generated as a result of that, and the process repeats for max, right? And so the tree alternates between max, chance, and min levels until you get to your terminal nodes, right? And so the terminal nodes represent a final position in the game, where you have one person winning or the other, and you can assign your usual utility values to those terminal nodes, right? So in the textbook, in their example, they assigned utility values of 2, -1, 1, -1, and 1, and so forth, as you can see at the bottom. And so again, we've got an abbreviated game tree that's taking random chance into consideration, right? So as I was saying, we're having each chance node, get dictated what they're going to generate based off of the probabilities of the die roll. Okay, now what we have, or what this means, is that there's uncertainty, right? So the only thing we can do is calculate a position's expected value. Okay, and so what is that? Well, that's going to be a computation that's the average of all possible outcomes of the chance nodes, right? So we can say, well, this is what we expect this position to be worth, or what the possibility is of this position being, based off of the average of all of the possible outcomes of those chance nodes, right? So we can say, okay, well, what could possibly be generated based off of this die roll, okay? And then we can make a calculation of the value based off of an average of those, right? So if the player rolled 6-5, then that would lead us to having to make a decision and say, okay, well, what do we expect could be the possible benefits here? And so we can average out, if we have a chance node here, we can average out and say, okay, well, based off of the possibilities that could result from that, based off of subsequent die rolls, we can come up with a number to generate these utility values, or these expected values. Okay, so what we want to do is we need a generalization of the deterministic game's minimax value, right? Because we have to come up with a generalization of the utility values of eventual positions, right? Based off of what the odds are. Okay, so if we're going to do that, we can say, all right, well, let's call it our expected minimax value, right? So for games that have chance nodes, we're going to modify that just a little bit. So the terminal nodes, the min and the max nodes, they stay the same under this modified algorithm, right? So for chance nodes, what you have to do is you have to sum the value of all the outcomes, and then you weight that using the probability, right? So this is what I was trying to say a second ago, is that when I'm trying to evaluate a position, when Max is trying to decide what moves it's going to make, or the best moves for it to make, given the random chance that your opponent could roll a certain set of dice, we have to be able to say, all right, well, if they rolled 5-6, right, then what are we going to do in response to that? Well, then we can say, well, let's take a look at the sum of all the potential terminal states, right, all those values, and then we can weight that based off of the probability that all the die rolls are going to come up to give us that final state, right? So, or that final set of states. Let me see if I can put it in another way here. If I roll a d6 and it comes up 3, right? In whatever game that we're playing. Now, in response, I'm going to take a move, right, based off of that die roll, right? Like I said, I roll a 5, okay? And then I'll go ahead and take my move but then in response, it's going to be your turn, and you're going to roll a die, right? And so, based on my die roll of 5, you might roll a 3 in response, right? Well, if you roll a 3 in response, well, then we can play this game recursively, right? And so, what I have to do is I have to consider, well, what are the odds that you're going to hit that 5, say, 10 times in a row? Or if you're going to hit a 5 and a 10 and then a 12 and then an 8, right? So through using that weighting, all of the terminal nodes that eventually could result from that combination of die rolls, I'm going to take their values, I'm going to sum those up, and then I'm going to weight that using the probability that I just laid out for you, right? So if the probability of you ending up in a particular state is the result of rolling 5 out of 6, 5 out of 6, 5 out of 6, 5 out of 6, 4 times in a row, well, then the utility of that is going to be diminished, because the odds of you actually getting those die rolls all in a row are going to be less, right? So we just have to take that into consideration. And so when you take a look at the expect the minimax function, that's what's being played out here, right? So you've got, from Max's point of view, what the maximum value is going to be based off of a series of results, right? From Min's point of view, you've got the minimum value that they're going to expect based off of a series of rolls, but then you've got modification of that based off of the sum of all of the probabilities, right? So we're taking into consideration all of the die rolls for all of the turns being played out until we get to a terminal state. That's the big idea. Okay, so since we do have these chance nodes that are cropping up, which enable us to take chance into consideration, the meaning of the evaluation values can be a bit more specious, a bit more dicey than they can be in deterministic games, right? So take a look at these two trees here, one on the left, one on the right, right? So depending on the odds, depending on the possibility or the probability of one result over another, right? Based off of those possibilities, then values are going to get skewed a bit, right? So if we take a look on the left-hand side, for example, right, the different odds that are laid out, we have a 90% chance of the result leading to Min's 2 node, and we have a 10% chance of the result leading to Min's 3 node, right? And then for move A2, and that was for move A1. For move A2, we'll end up having the chance of choosing this 1 node to be this 1 value Min move to be 90%, and then the chance of choosing the 4 valued position to be 10%. So what does that mean? Well, if you look at the chance node values, you've got 2.1 on the left hand side and you've got 1.3 on the right side. And so what you end up with is a weighted expected value for the move corresponding to A1 of 2.1, right? So that's going to dictate that Max makes that choice, that it goes with action 1, because the expected value is going to be higher because of the combination of the weighting, right, 0.9 and 0.1, and or on the expected values of the terminal states at the very bottom here, right? So I've got an expected value of 2.1 based off of the weighting of the value of the 2 position, the 3 position. There's a 90% chance of me hitting the 2, there's only a 10% chance of hitting me the 3, so combining those numbers, that gives me an expected value of 2.1, so I'm going to go with that. Even though if you look over at the potential results, or the best position, right, that I could take would be Min's 4 weighted position over here, right? But the thing is that 4 weighted position, there's only a 10% chance of me getting there if I were to choose, or if Max were to choose A2, right? If Max were to choose A2, then there's a 90% chance that they end up at the 1 valued position, which is worse than either the 2 or 3 had they chosen A1. So the chances of getting into a better position by taking A2, that 4 valued position, is really, really small. So this algorithm is going to select the A1 position, even though it's almost going to certainly guarantee, or it will guarantee, that they're going to miss out on the best overall position, which is the 4 position from Min's point of view, right? So we're going to end up choosing A1. Now, if you take a look on the right-hand side, things change a little bit, right? Because now, if you look at the values and the weights, right, the percentages are still the same. There's a 90% chance of ending up going down the left path, or the left subtree from the 21 valued chance node, and there's a 10% chance to go to the right, and there's 90% chance to go left, 10% to go right. But if you take a look at the weightings of the terminal states, right, that dictates an overall value on Min's possible moves, or the states outlined on the Min row. We've got a value of 20 here, a value of 30 here. There's a 90% chance of hitting 20 and a 10% chance of hitting 30. But if you come over on the A2 move, there's a 90% chance of hitting 1. Now only a 10% chance of hitting 400. But the value of that 400 position is so much that even with the weighting, the A2 position has a way better expected value of 40.9. So in that case, it would be best for Max to actually choose to take the A2 action, and so that's what it's going to do. Now, even though there's only a 10% chance of hitting the position that's 400, or worth 400 from Max's point of view, the payoff is just too great to ignore. And so, the algorithm's going to say, well, go ahead and select action 2. So hopefully that was okay. I mean, hopefully you understood it, because we've got, again, just to summarize, the chance nodes are giving us a expected value, which is computed based off of the weights of the chances, 90%, 10%, of Min being able to hit either this state, the 2 state, or the 3 state. And similarly, there's a expected value of 1.3 based off of the 90% chance that Min is going to hit the 1 state here, or the 10% chance of hitting the 4 state here. And so Max is going to choose action 1 because the expected value is better. The expected result, no matter what Min rolls, is better than the expected result of of action 2, depending on what Min rolls, the 90% hitting the 1, or the 10% hit the 4. And the similarly over on the right hand side here, scenario, I guess you could say B, right? The expected value of taking action 1 is only 21, which is derived from the percentage, the 90% chance of getting to the 20 position, or the 10% chance of getting to the 30 position. A2, there's an expected value of 40.9, which again is derived from the 90% chance of hitting the 1 value position, as opposed to the 10% chance of hitting the 400 value position. Okay, so what's Max going to choose? Going to make that choice based off of the expected value as outlined by the chance node, and that chance node's expected value is computed or derived based off of the chance of Min rolling 90% or 10% to get to the 20 or the 30 valued state. So that sounds a lot more complex than it actually is. So hopefully I didn't lose you too hard in that description. Hopefully I made it clear enough. If not, give me a holler, let me know, and I'll be happy to go over it with you again. Okay, so dealing with this, right? Dealing with this is going to require studying some probability or some additional mathy kind of stuff. So if you've had your statistics class already dealing with probability, awesome. Then you probably can wrap your head around this a little bit more easily. If not, well, dealing with that is going to involve the linear transformation of win probability over a position. In chapter 16 digs into that in more detail. But if I was to summarize, just to, again, to give you the big idea, the big overview, is that, look, we have to take die rolls into consideration, and that's what these chance nodes are allowing us to do. Because Max is going to have to choose between a move, action 1 or action 2, and based off of the choice that Max makes, well, Min's going to have to roll a die here, and there's a 90% chance of it coming up a certain value, which would lead to Min choosing this board state, or a 10% chance of Min choosing this board state. So if I choose action 1, there's a 90% chance Min's going to end up here, or a 10% chance that Min's going to end up here. Using that weighting and those odds, I got my expected value of 2.1, which is going to be better than that expected value of 1.3, applying that exact same reasoning to action 2. So Max should take action 1, because no matter what Min rolls, I'm going to end up, odds are, I'm going to end up in a better position than if I chose action 2. Alright, so some performance things here. If the program knows all the die rolls ahead of time, it doesn't, but assuming that it did, then what's your performance? Big O of B to the M, where B is the branching factor, M is the max depth, right? So not very good, right? It becomes even worse than that, though, because you have to consider chance nodes also. So you have to multiply that B to the M times N to the M, where N is the number of dice rolls that happens, right? So consider the performance here. Backgammon is going to have a branching factor of about 20, right? And a number of die rolls of about 21 to be able to get to terminal states, right? That's going to be the depth there. Sometimes B can be as many as 4,000, or as much as 4,000. So that means how many plies can we actually have? Usually it's going to be about 3. Okay. Now we can improve performance by quite a bit. We can have something kind of like alpha beta pruning if we put bounds on the different possible utility values. For example, if we say, well, all the utility values are between -2 and +2. What that means is that the values on those leaf nodes have a bound, right? What that means is that they can't be greater than +2 or -2. So what that means is that any terminal nodes, any terminal states that have values less than that or greater than that, well, we're just pruning them. We're not considering them anymore, right? So that cuts down on the total number of game states that we actually have to generate, because we're not going to generate any subsequent states off of states that have values less than -2 or greater than +2. So that's going to cut off a lot of the branches of our game tree. Okay, let's see here. So what's an alternative? An alternative is the so-called Monte Carlo simulation the textbook talks about. So what this has to do with is how you evaluate positions, right? So you can come up with a scoring system like we've talked about before, but another way that you can come up with a scoring system, how you value positions, is essentially starting with that alpha beta algorithm, right? Use the alpha beta algorithm, and what you do is you play as many games as you can against yourself using random dice, right? And so by doing that, that allows you to have a particular win percentage, right? So you can say, you can generate a full tree saying, well, if the user had rolled this, or if the user had rolled that, if the user had rolled the other thing, play out all the games using those random dice rolls. And what that can do is that can provide you a particular win percentage that you can use as a heuristic, right? So if you have the computer play against itself and you just say, all right, well, we'll take a little bit of the randomness out by just saying, okay, well, go ahead and play if they had done 1 out of 6, if they had done 1 out of 2 out of 6, 3 out of 6, 4 out of 6, 5 out of 6, whatever. Basically just play games against yourself, right? In a deterministic fashion. And by doing that, you can come up with a win percentage, and then you can use that win percentage as a heuristic. And so once you have that win percentage, you can say, all right, well, fine, then taking this particular move when the dice rolls come up 5 and 6, leads to a 90% chance of winning or an 80% chance of winning. So I'm going to take it, as opposed to another position where if the die rolls came up 3 out of 4, maybe there's only a 20% chance of winning. Okay, fine, right? So there's a term here. I mean, that works pretty good for backgammon. Just have backgammon play against itself. Have the AI play against itself 10,000 times, and then keep track, keep statistics, see what moves lead to a higher winning percentage. Fine. Now, whenever you have games that are using dice, there's a term here. What we're talking about here is termed a rollout, or referred to as a rollout. Okay. All right. So, again, what you're doing, just to summarize, Stochastic Games, you have to modify the alpha or the Minimax algorithm, and you have to take die rolls into consideration. And the way you do that is by adding these chance nodes, and these chance nodes can generate positions that men could take and the odds that they're going to take them, and you weight each position based off an expected value, taking into consideration a chain of die rolls and probabilities. Okay, and you can make this more efficient by placing bounds on certain utility values, or using certain utility values for terminal nodes. Okay, so and then one way you can improve your heuristic is you can, or your value for certain positions, for certain terminal nodes, just play against yourself, right? And that's called the Monte Carlo simulation. Use those winning percentages to be able to value certain moves based off of certain die rolls.